look at something near you. The wall, your own hand, a single point of light in the dark. It takes no effort. You have done it countless times today without once thinking about it. And yet, in the instant you looked, something happened that no one on earth can fully explain. Something that has resisted the combined effort of the greatest physicists who ever lived for 100 years. Something that sits, still unsolved, at the very center of the most successful theory of reality our species has ever built. Here is the strangeness, in its barest form. A tiny piece of the world, an electron, a particle of light, a single atom, when nothing is watching it, does not behave like a definite thing in a definite place. It behaves like a spread of possibilities, a haze of every path it might take and every place it might be, all of them somehow present at once, overlapping, undecided. The mathematics that describes this haze is exact, elegant, and astonishingly accurate. It has never once been found wrong in a century of the most demanding tests ever devised. And it says, without the slightest ambiguity, that the little piece of the world is not in any single state, but in all of its possible states together, smeared across every option it has. And then you look, you make a measurement, and in that instant the haze is gone. The spread of possibilities vanishes, and in its place there is one definite outcome, one position, one result, sharp and singular and real. The electron, which a moment before was everywhere it could be, is now simply somewhere. The many have become one. And nothing in all of mathematics explains why looking did that. The equations describe the haze perfectly. They do not contain a single line that tells you why, or how, or even precisely when the haze should resolve itself into a fact. The most exact theory human beings have ever written down has, at its very heart, a step it cannot justify, a moment it cannot describe, set off by something it cannot define. That something is called observation, and after 100 years, we still do not know what it is. So tonight we are going to settle in beside that mystery, slowly, with no obligation to solve it because no one has been able to. We are going to learn just enough of how the theory works to feel exactly where it breaks. We are going to walk through the answers that brilliant people have offered across the last century, and we are going to see the steep and strange price that each of them demands. And we are going to arrive, gently, at the quiet and unsettling truth that the world as the equations describe it is not the world as you are living in it right now, and that the gap between the two has not been closed by anyone despite 100 years of trying. Let your eyes rest. Let your appearance soften. The deepest unsolved problem in all of physics is not somewhere far away at the edge of the universe. It is here, in this room, in the simple act of seeing. To feel where the theory breaks, you first have to understand how it works, and the heart of how it works is a single mathematical object with a strange and wonderful character. Physicists call it the wave function. It is not a thing you can see or touch. It is a description, a piece of mathematics that carries within it everything that can be known about a quantum system, every possibility open to it and how much each possibility counts. If you want to describe an electron, you do not give its position, because before you measure it, the electron does not have a single position. You give its wave function, and the wave function spreads across all the places the electron might be found, assigning to each one a certain weight, a certain strength of possibility. The wave function is the haze made precise. It is the exact mathematical shape of the cloud of maybes. Pause on how unfamiliar an object this is, because nothing in ordinary life behaves like it. A rock has a position. A thrown ball follows a single path. Even when we are uncertain about where something is, we assume it is somewhere definite and we simply do not yet know which place. The wave function is not like that. It is not a confession of ignorance about a hidden definite position. It is the full and complete description of the system, the very most that can in principle be known, and that fullest possible description still refuses to place the electron anywhere in particular. The electron, described as completely as the laws of nature allow, is not secretly here while we guess. It is genuinely spread, genuinely indefinite, its location not merely unknown but unfixed, a question that has no answer until the question is forced. This is the first deep strangeness, and everything that follows grows out of it. The most complete account of a quantum thing is an account of what it might be, not what it is, and the might is not a gap in our knowledge, but a feature of the thing itself. And this wave function does something remarkable. It changes over time, and it changes according to a rule so clean and so dependable that it stands as one of the great achievements of the human mind. The rule is an equation, written down in the 1920s, that governs how the wave function evolves from one moment to the next. Give the equation the wave function now, and it will tell you the wave function at any future moment, exactly, with no uncertainty whatsoever about the evolution itself. The cloud of possibilities flows forward in time as smoothly and as predictably as the hands of a perfect clock. There is nothing random in this flow, nothing abrupt, nothing left to chance. The equation is continuous, which means it never jumps. It is deterministic, which means the future shape of the haze is fixed entirely by its present shape. And it is reversible, which means that just as the equation can carry the wave function forward, it can carry it backward, reconstructing the past from the present without losing a thing. This smooth, lawful, reversible flow is the first of the two rules at the center of our story, and it is the rule that quantum mechanics offers as its fundamental description of how the world changes when no one is looking. It is worth admiring just how complete and rigid this first rule is, because its very perfection is what makes the rest of the story so hard. There is no slack in it, no looseness, no room for chance. If you knew the wave function of the entire universe at one moment, this rule would, in principle, tell you the wave function of the entire universe at every other moment, past and future alike, with absolute exactness. It is as deterministic as anything in the older physics, more so than the weather, more so even than the orbits of the planets, which suffer tiny perturbations. The smooth evolution of the wave function is clockwork of the purest kind. Whatever randomness, whatever uncertainty, whatever unpredictability we associate with the quantum world, none of it lives here in the first rule. The first rule is serene, lawful, and entirely predictable. The strangeness, when it comes, does not come from the equation that governs the haze. It comes from what happens when we try to look at the haze, and that is a different matter entirely, governed by a different rule of an utterly different character. Now, the wave function can hold more than one possibility at the same time, and this is the feature that makes the quantum world so unlike the world of our experience. A quantum system can be in what is called a superposition, a combination of states that, in ordinary life, would seem to exclude one another. An electron can be in a superposition of being here and being there, its wave function carrying both locations at once. A particle can be spinning in two opposite directions at the same time, the two combined into a single quantum state. This is not a statement about our ignorance, not merely a way of saying we do not yet know which state the system is in. Mathematics insists that the system is genuinely in both, that both possibilities are really present, woven together in the one wave function, until the moment something forces a choice. To make this concrete, take the simplest quantum system there is, a single particle carrying a property called spin, which for our purposes can be pictured as pointing either up or down. In the ordinary way of thinking, it must be one or the other. Quantum mechanically, it can be in a superposition of up and down together, the two combined in its wave function with whatever weights you please. And this is not a hidden fact awaiting discovery. If you prepare such a particle and then measure its spin along a different direction, the results you get could not be produced by a particle that secretly was up all along, or secretly down. The pattern of outcomes only makes sense if the particle truly held both at once before you asked. The superposition is woven into how the particle answers every possible question you might pose to it, and there is no way to reproduce that behavior with a particle that was quietly definite the whole time. Both states are genuinely present until a measurement forces the system to surrender one of them. And we know this is more than mathematical bookkeeping, because superposition leaves fingerprints in the real world that nothing else could leave. The most famous demonstration sends individual particles, one at a time, toward a barrier with two narrow openings in it, and lets them land on a screen beyond. If each particle went through one opening or the other, like a tiny pellet, the pattern building up on the screen would be simple, just two bands of impacts behind the two openings. But that is not what happens. What builds up instead is a pattern of many bright and dark stripes, the unmistakable signature of waves overlapping, reinforcing in some places and canceling in others. Each single particle, it turns out, passes through both openings at once, its wave function spreading through both and interfering with itself on the far side. Send the particles one by one, with long gaps between them so that none can possibly affect another, and still the striped pattern slowly assembles, impact by impact. Each particle interferes only with itself, with the spread of its own possibilities. Superposition is real. The haze is real. A single particle really does explore all of its options at once, and the overlapping of those options shapes where it is allowed to land. But here is the thing that brings us to the edge of the mystery. When you actually look, when you place a detector at one of the openings to catch the particle in the act of passing through, you never find a particle spread across both. You find it at one opening or the other, whole and definite, a single particle in a single place. And the moment you do, the striped pattern on the far screen vanishes, replaced by the two simple bands you would expect from ordinary pellets. The act of detecting which path the particle took destroys the interference, collapses the spread of possibilities, and leaves behind a single, definite fact. The haze observed becomes a thing. This is the second behavior, the one the smooth equation does not contain, and to make the theory actually predict what detectors show, physicists had to add a separate rule by hand. Notice already how slippery the trigger is. The interference vanished not, it seems, because a conscious person looked, but because a physical detector at the opening recorded which way the particle went. Block that recording, keep the path information from ever being registered anywhere, and the interference returns, even if a person was watching the screen the whole time. Allow the path to be recorded, even by a lifeless instrument that no one ever reads, and the interference is gone. So, whatever observation means here, it is not obviously about minds or awareness. It seems to be about the world coming to hold a record of an outcome, somewhere, in some physical form. But that only deepens the puzzle, because it does not tell us what counts as a record, how complete it must be, or why the mere existence of information somewhere should reach back and change what the particle was allowed to do. The trigger for the haze becoming a fact is real and reproducible, and we still cannot say clearly what the trigger is. That separate rule is how the theory connects its haze of possibilities to the definite numbers that come out of real experiments. It is called the Born rule, after the physicist who first stated it, and it is beautifully simple to use and deeply strange to think about. The wave function assigns a certain weight to each possible outcome. The Born rule says that when you measure, the probability of getting any particular outcome is found from the square of that weight. The larger the weight a possibility carries in the wave function, the more likely you are to find it when you look. This rule is the bridge between the theory and the world, the place where the smooth spreading haze is converted into odds, into the relative frequencies of definite results that experiments actually record, and it works flawlessly. Apply the smooth equation to evolve the wave function, then apply the Born rule to read off the probabilities of measurement, and you can predict the behavior of atoms and particles and light to a precision that beggars belief, agreement between theory and experiment so exact that it is like predicting the distance across a continent and being right to the width of a hair. There is something quietly profound buried in that rule, easy to use and easy to pass over. Notice that quantum mechanics, for all its precision, does not predict what will happen. It predicts only how likely each thing is to happen. Run the identical experiment twice. Prepare the system in exactly the same wave function. Measure it in exactly the same way, and you may get different results, with no difference in the setup to account for the difference in outcome. The theory does not merely fail to tell you which outcome you will get. It insists that the outcome is not fixed in advance by anything at all, that two perfectly identical situations can yield two different facts, and that only the odds, never the result, can be foreseen. This is a break with everything the older physics promised. The old picture said that if you knew the present completely, the future was determined. Quantum mechanics, through this rule, says that even a complete knowledge of the present leaves the particular outcome genuinely open, settled only when the measurement happens, and settled then by nothing the theory can point to. This is the working picture of quantum mechanics, the operational machine that physicists run every day without a second thought. You write down the wave function, you let it evolve smoothly according to the equation, and when a measurement happens, you use the Born rule to compute the chances of each outcome, and you find that nature obeys those chances exactly. On this machine rests an enormous fraction of the modern world. The behavior of every transistor in every computer, the light of every laser, the chemistry of every material, the stability of every atom in your body, all of it is governed by these rules, and the rules have never failed. Quantum mechanics is, by any measure of predictive success, the most thoroughly confirmed theory in the history of science. You could be forgiven for thinking that a theory this successful must be completely understood. It is not, because hidden inside that smooth operational picture, right at the point where the haze becomes a fact, is a crack that runs all the way to the foundations, and once you see it, you cannot unsee it. For most of the people who use quantum mechanics, this is exactly where the matter rests, and rests comfortably. There is a long and respectable tradition in physics of treating the theory as a machine, for producing predictions and declining, firmly, to ask what lies beneath it. Feed in the setup, turn the crank of the equation and the rule, read off the probabilities, compare with experiment, and marvel that it always works. The questions about what is really happening, about what the wave function is and what observation does, get set aside as philosophy, as idle, as the kind of thing that distracts from real work. And, as a practical matter, this attitude is entirely defensible. You do not need to know what the theory means in order to use it flawlessly, any more than you need to understand an engine in order to drive. But the questions do not vanish merely because they are set aside. They wait, patiently, beneath the smooth surface of the working theory, and the moment you ask them honestly, the crack reopens, exactly as wide as it ever was. The crack is this. The theory contains not one rule, but two, and the two rules describe two completely different kinds of behavior, and nothing in the theory explains how or when one gives way to the other. The first rule is the smooth equation, the lawful flow of the wave function, continuous and deterministic and reversible, the rule that governs the system whenever no one is measuring it. The second rule is collapse, the abrupt event in which the spread of possibilities suddenly reduces to a single definite outcome, the haze snapping into a fact the moment a measurement is made. These two rules could hardly be more different in character. The first is continuous, the second is a jump. The first is deterministic, fixing the future exactly, while the second is random, delivering one outcome out of many according to mere probabilities. The first is reversible, able to run forward or backward without loss, while the second is irreversible, erasing all the possibilities that did not happen as though they had never been. One rule is a smooth river, the other is a sudden cliff, and the theory simply sets them side by side, with no account of where the river ends and the cliff begins. And it is not as though the two rules merely sit awkwardly together while secretly being compatible underneath. Taken literally, they contradict each other about the same events. Consider a single measurement. The smooth rule, applied to the system and the measuring device together, says the combined arrangement evolves into a superposition, the device entangled with the system, every possible reading present at once, no single result anywhere. The collapse rule says that instead one reading occurs, chosen at random, the others annihilated. These are not two descriptions of different things. They are two descriptions of the very same physical event, the same interaction between the same system and the same device, and they flatly disagree about what happens. One says many, the other says one. One says smooth and reversible, the other says abrupt and final. They cannot both be the literal truth about that interaction. At most, one of them can be fundamental, and the other must somehow emerge from it, and the entire difficulty is that no one has ever shown how. The theory hands you both rules, tells you when to use each by a vague appeal to whether a measurement has occurred, and never explains how the second could possibly follow from the first. Sit with how peculiar this is. A measuring device, after all, is not some magical object standing outside of physics. It is a piece of the world like any other, made of atoms, built from the same particles that everything else is built from. And those atoms and particles are themselves governed by quantum mechanics, by the smooth first rule. A detector catching a particle is just a very large collection of quantum systems interacting with a small one. So why, when this large quantum system interacts with the small one, does the smooth rule suddenly stop applying and the collapse rule takes over? If everything is quantum, if the detector is quantum and the particle is quantum, and the physicist watching the detector is quantum, then the smooth equation should govern the whole arrangement, all of it together, with no collapse anywhere. The honest application of the first rule to the entire situation, particle and detector and observer alike, never produces a single definite outcome. It produces an ever larger superposition, the spread of possibilities growing to engulf the detector, and then the room, and then everyone in it. The first rule, followed faithfully, never collapses anything. And yet collapse is exactly what we see. The detector reads one value, the world delivers one fact. Something happens that the fundamental rule does not contain. There is a name for the place where physicists, in practice, draw the line. The spot in the chain where they stop applying the smooth rule and start applying collapse. It is sometimes called the cut, the division between the quantum system being studied and the classical apparatus doing the studying. In actual practice, the cut is placed by judgment and convenience, somewhere comfortably between the small thing of interest and the large familiar world of laboratory equipment, and wherever it is placed, the predictions come out right. But that practical success hides a scandal. The theory contains no instruction for where the cut belongs. You can slide it inward, treating more and more of the apparatus as quantum, and the predictions do not change. You can slide it outward, treating more of the world as classical, and they do not change either. The cut can be placed almost anywhere, and the working theory will not complain, which sounds like flexibility, but is really a confession. A fundamental theory should not contain a movable, undefined boundary between the part of the world it describes one way and the part it describes another. The freedom to put the cut anywhere is the freedom of a theory that does not know where its two rules actually meet. This is the measurement problem, and you can sharpen it until it becomes almost unbearable. Imagine following the chain of interactions outward. The particle is in a superposition. It strikes the detector, and now, by the smooth rule, the detector is in a superposition too, its needle pointing at several readings at once. The light bouncing off the detector carries that superposition to your eye, and now your eye is in a superposition. The signal travels to your brain, and now your brain is in a superposition, holding several perceptions at once. Where, in this chain, does the collapse happen? Where does the spread of possibilities finally become a single fact? At the detector, at the eye, in the brain, at the threshold of awareness. The mathematics gives no answer. You can place the dividing line, the boundary between the smooth quantum world and the definite classical one, anywhere along the chain you like, and the theory will not object because the theory does not tell you where the line belongs. The boundary is movable, undefined, placed by hand wherever the physicist finds it convenient, and nowhere does the formalism say where it truly lies. There is no principled cut between the part of the world that spreads into possibility and the part that delivers facts. The strangeness of this was captured, early on, in a thought experiment so vivid that it has never been forgotten, an image of a cat whose fate is tied to a single quantum event. Picture a cat sealed in a box, and inside the box a device that will release a poison if, and only if, a single quantum system, say a radioactive atom, happens to decay. The atom, left to itself, evolves into a superposition of having decayed and not having decayed, both possibilities present in its wave function at once. But the atom is linked to the device, and the device to the poison, and the poison to the cat. So if we take the smooth rule seriously, and apply it honestly to the whole sealed box, the superposition spreads up the chain. The atom is decayed and not decayed. The poison is released and not released. And the cat, monstrously, is both alive and dead at the same time, a living cat and a dead cat superposed into one quantum state, waiting inside the box until someone opens it and looks. The point of the image is not that anyone believes a cat can really be both alive and dead. The point is that the formalism, followed without the collapse rule, leads straight to that absurdity, and that the collapse rule, which saves us from it, is added with no justification, triggered by an act of observation that the theory cannot define. Open the box, look at the cat, and somehow the superposition resolves into one outcome, alive or dead. But the theory cannot tell you why opening the box does what smooth evolution refuses to do. No derivation connects the two rules. No equation turns the river into the cliff. The collapse is a postulate, bolted onto the smooth mathematics, because without it the theory does not match what we see, and with it the theory works perfectly and means nothing anyone can agree on. You can push the chain further still, and the early architects of the theory did, following it to a conclusion that borders on the absurd and was meant to. If the detector inherits the superposition, and the eye inherits it from the detector, and the brain inherits it from the eye, then perhaps collapse waits all the way at the very end of the chain, at the threshold of conscious awareness, as though it were the act of a mind taking notice that finally forces the haze to become a fact. Some serious thinkers entertained exactly this, that consciousness itself is the missing ingredient, the thing that collapses the wave. It is a striking idea, and a deeply uncomfortable one, because it would place mind at the foundation of physical reality, and because it raises at once the question of what counts as a conscious observer, and whether a cat qualifies, or an insect, or a recording instrument with no principled place to stop. Most physicists recoil from it, and it is far from the mainstream view. But the bare fact that the formalism permits the chain to be followed that far, with nothing in the mathematics to halt it sooner, shows how thoroughly the theory fails to specify where and how the definite world comes to be. The collapse can be placed at the detector, or the eye, or the mind, and the equations object to none of these, because the equations say nothing about collapse at all. For 100 years, the finest minds in physics have tried to make sense of this, and the attempts have crystallized into a handful of distinct positions, the great interpretations of quantum mechanics. Each of them keeps the mathematics intact, because the mathematics works, and each of them tells a different story about what the mathematics means and what is really happening when the haze becomes a fact. And here is the humbling part, the thing that makes the measurement problem so durable. Every single one of these interpretations solves the puzzle only by paying a steep and painful price somewhere else. Each one buys clarity in one place by surrendering something precious in another. There is no free interpretation, no story that keeps everything we want to keep. After a century, the disagreement is not about the equations, which everyone shares, but about which sacrifice is the least unbearable, and on that question there is no consensus at all. It is tempting to hope that one of these positions is simply correct and the others simply mistaken, that the disagreement is the ordinary churn of science before the truth wins out. But that is not quite the situation. The positions are not competing guesses about a fact that further work will decide. They are different ways of paying an unavoidable bill. The bare mathematics, plus the plain fact that we experience single definite outcomes, leaves a debt that must be settled somehow, and each interpretation settles it by surrendering a different thing we would rather keep, a definite reality, or a single world, or locality, or the completeness of the equation. You can choose which to give up. You cannot keep them all. So as we walk through them, listen less for which one is right and more for what each one is willing to lose, because the losing is the real content. The choice among interpretations is, at bottom, a choice about which beloved feature of the world you are most willing to live without. The oldest of these positions takes the boldest route. It chooses, in effect, to deny that there is any deeper question to answer. In this view, the wave function is not a real thing spread out in the world. It is a tool, a piece of mathematics that encodes what we can predict about the outcomes of measurements, nothing more. The smooth equation describes how our predictions evolve. The collapse describes how we update those predictions the moment a measurement gives us new information. There is no mysterious physical event when the haze becomes a fact, because the haze was never a physical thing to begin with. It was always just our knowledge, and knowledge can change in a jump when we learn something new. Asking what is really happening to the system between measurements, in this view, is a meaningless question, a confusion, the kind of thing a serious physicist should refuse to ask. The world at the level of measurements is definite and classical, and the quantum haze is only our predictive machinery for those measurements. This position has the great virtue of letting you get on with the work, calculating and predicting without worrying about what it all means, and for that reason it dominated physics for generations. But its price is severe. It declines to tell you what reality is doing. It draws a line between the quantum and the classical and treats that line as fundamental without ever saying where it lies or why. It takes measurement, the very thing we most want explained, and treats it as a primitive, unanalyzable act, a place where the theory simply stops. It does not solve the measurement problem, it refuses to regard it as a problem. And many find that refusal not a solution but an evasion, a decision to look away from the deepest question precisely where it becomes most pressing. It is fair to add, in its defense, that this position was held by some of the very people who built the theory, and that they held it not out of laziness but out of a hard-won conviction that the quantum world simply does not admit the kind of picture we instinctively demand. The lesson they drew was that our intuitive notion of a definite reality unfolding independently of any observation is a prejudice inherited from the large, slow world we evolved in, and that the quantum realm owes us no such picture. Reality, in this view, is not a thing the theory describes, but a thing that shows up only in the answers to our measurements, and to ask for more is to ask for something nature simply does not provide. Whether that is wisdom or surrender has been argued for 100 years, and the argument is not settled. A second position takes the opposite path. It says, let us take the smooth equation absolutely seriously, more seriously than anyone has dared. Let us assume that the first rule is the only rule, that the wave function is real and that it never, ever collapses. The smooth evolution is all there is. But then, the alive and dead cat, the detector pointing at every reading at once, the brain holding several perceptions together, all of these superpositions are real and they never resolve. So why do you, the observer, only ever experience one outcome? The answer this position gives is breathtaking in its boldness. You experience only one outcome because you, too, have split. When the measurement happens, the world does not select one possibility and discard the rest. Instead, the whole world branches, dividing into separate strands, one for each possible outcome, every one of them equally real. In one branch, the cat is alive, and the version of you in that branch sees a living cat. In another branch, the cat is dead, and another version of you sees a dead cat. Both are real. Both happen. There is no collapse, no selection, no loss, only an endless branching of reality into ever more parallel strands, each containing its own observers, seeing their own definite outcomes, all of them descended from the smooth, unbroken evolution of the single universal wave function. This view dissolves the measurement problem cleanly. There is no mysterious collapse because there is no collapse at all, only branching, and branching follows from the smooth rule with nothing added. But the price is staggering, perhaps the most extravagant price ever asked by a physical theory. It demands that you accept an unimaginable, ever-growing multitude of parallel realities, countless versions of every observer and every object and every event, almost all of them forever beyond observation, brought into being constantly by every quantum interaction everywhere. And it struggles with a subtle question that will not go away. If every outcome happens, in what sense are some outcomes more probable than others, as the born rule insists they are? What does probability even mean when nothing is left out, when every possibility is realized in some branch? Mathematics is preserved, reality is made deterministic and whole, but the cost is a cosmos of unobservable multiplicity and a lingering puzzle about the meaning of chance. What makes this position so hard to dismiss, despite its extravagance, is that it adds nothing to mathematics and removes the one thing that never belonged there. It takes the smooth equation, the rule everyone agrees on, and simply refuses to append the collapse rule that everyone admits was bolted on by hand. In that sense, it is the most conservative reading of the bare formalism, the one that takes the equations literally and follows them wherever they lead. The countless parallel branches are not an extra assumption added to the theory. They are what the theory says, if you believe the smooth rule and nothing else. The extravagance, its defenders point out, is not in the interpretation, but in the equation itself, and the only question is whether you are willing to believe the equation completely. Many cannot. The cost in unseen worlds feels too high, the meaning of probability too strained. But the position endures because it is, in a strict sense, what you get by trusting the mathematics and adding nothing to it. A third position refuses both the evasion of the first and the multiplication of the second, and tries instead to restore the comfortable picture of a single definite world in which particles have real positions at all times. In this view, the haze is real, the wave function exists and spreads and evolves by the smooth rule. But it is not the whole story. Alongside the wave, there are the particles themselves, actual particles with definite locations, always, whether anyone is looking or not. The wave function does not contain the particle as a spread of possibilities. Instead, it acts as a kind of guide, a field that pushes and steers the particle along a definite path, telling it where to go. The particle always has a real position, the wave merely directs it. There is no collapse, because the particle was never spread out in the first place. When you measure, you simply find the particle where it already was, guided there by the wave. This view restores everything our intuition craves. Reality is single and definite. Particles are real and located. The world is deterministic, its future fixed by its present, with no dice thrown anywhere. It even reproduces all the predictions of standard quantum mechanics exactly, but it too exacts a heavy toll, and the toll is one of the deepest in all of physics. For the guiding wave to push the particles in just the way needed to match experiment, it must connect them instantaneously across any distance. A measurement performed here must influence, at once, with no delay whatsoever, a particle arbitrarily far away. This is not a flaw that careful work could remove. A profound theorem, proved in the 1960s and confirmed in experiment after experiment since, shows that any theory which restores definite underlying values to quantum systems and still matches the predictions of quantum mechanics must contain exactly this kind of instantaneous connection across space. The price of a single, definite, deterministic reality is that reality must be woven together by influences that leap across any gulf in no time at all, in deep tension with the spirit of relativity, which holds that nothing should outrun light. You may have your definite world, but only if you accept that it is stitched together by threads faster than anything should be. This result, that any attempt to restore definite underlying reality must be paid for with instantaneous connection across space, is one of the most profound discoveries in the history of physics, because it closes a door that for decades seemed open. Many had hoped that the strangeness of quantum mechanics was a sign of incompleteness, that beneath the haze there were ordinary hidden details, definite all along, and that a deeper theory would one day reveal them and restore the comfortable classical world. The theorem proved that this hope cannot be satisfied in the way one would want. You may have your hidden definite reality, but only at the cost of accepting connections that span any distance in no time at all, a feature so strange that it merely trades one kind of weirdness for another. The experiments that followed, performed with ever greater care over decades, confirmed it again and again. Nature really does refuse to be both definite and local at once. Whatever the world is, it is not the tidy local mechanism of classical intuition. That much, at least, is certain, even as everything else remains in dispute. And there is a fourth idea, the one that for a time seemed as though it might dissolve the whole problem without any of these terrible prices, and it is worth introducing here only to say that we will return to it, because it deserves a closer and more careful look than the others. It does not begin from a philosophical stance about what is real. It begins from a piece of ordinary physics, the simple fact that nothing in the world is ever truly alone. We will come to it shortly, and we will see that it accomplishes something genuine and important, and that it was widely embraced as the answer, and that it is, in the end, not quite the answer it appeared to be. But hold it aside for now, and notice what the first three positions have in common. Each one keeps the unbreakable mathematics. Each one tells a coherent story, and each one, to tell that story, gives up something we did not want to lose. The first gives up the very idea that the theory describes a reality at all. The second keeps reality but shatters it into countless unseen copies. The third keeps a single reality but binds it with impossible instantaneous threads. There is no option on the table that costs nothing. 100 years of the most careful thought have not produced a painless answer, and the persistence of the disagreement among people of the highest brilliance and the deepest seriousness is itself a measure of how hard the problem truly is. It is worth dwelling for a moment on the strangeness of this stalemate, because it is unlike almost anything else in science. Usually, when experts disagree, more data settles the matter. A better telescope, a finer experiment, a more precise measurement tips the balance and the disagreement resolves. But here, the disagreement cannot be settled that way, because all of the interpretations make exactly the same predictions for every possible experiment. They share the same mathematics. They differ only in the story they tell about what that mathematics means, about what is real behind the predictions, and no experiment can reach behind the predictions to check the story. Two physicists can agree on every number, run every experiment together, never once disagree about what the apparatus will show, and still hold flatly contradictory views about what the world is. The disagreement is real, and it is about reality itself, and it is, by the very structure of the theory, beyond the reach of the usual court of appeal. That is why 100 years has not resolved it. The thing in dispute is precisely the thing the theory refuses to talk about. Now we can return to that fourth idea, the one that promised, for a while, to make the whole difficulty melt away. It is called decoherence, and it grew up in the latter part of the 20th century, and it rests on an observation so obvious that it is easy to overlook its power. Nothing in the real world is ever isolated. The particle in the thought experiment, alone in the dark, is an idealization that never occurs. Every real object is constantly bathed in its surroundings, struck by stray photons of light, jostled by air molecules, warmed by the radiation of everything around it, touched at every instant by an environment of unimaginable richness and complexity. And here is the crucial point. Every one of these tiny interactions is itself a kind of measurement. When a stray photon bounces off our quantum system, it carries away information about that system, becoming entangled with it, linked to its state. One photon, then another, then countless more, each one entangling itself with the system and flying off into the environment, spreading the information about the system's state across an ever-widening web of particles that can never be gathered back together. There is a useful way to picture what this entanglement accomplishes, and what it does not. Before the environment intrudes, the superposition is like a private exchange between the possibilities, held within the system alone, where they can meet and overlap and interfere. The intrusion of the environment is like that exchange being overheard, copied, and broadcast to an enormous crowd of listeners, each photon and molecule carrying off a record of which possibility is which. Once the information of which is which has been copied into the environment in this way, the possibilities can no longer meet privately. To make them interfere again, you would have to gather back every scrap of that information from every photon and molecule that carried it away, reuniting the entire scattered environment perfectly, and that is, for any large system, so completely impossible that it never happens, not once in the whole age of the universe. The interference is not destroyed in principle, it is dispersed beyond any hope of recovery, and dispersed beyond recovery is, for every practical purpose, the same as gone. What this constant entanglement does to a superposition is subtle and decisive. Recall that what makes a superposition visibly quantum, what produces the striped interference pattern, is the delicate overlap between its possibilities, their ability to combine and reinforce and cancel. That overlap is fragile. It survives only as long as the possibilities remain cleanly separate from everything else. But once the system becomes entangled with a vast environment, once the information about which possibility is which has leaked out into countless photons and molecules scattering in all directions, the overlap between the possibilities is no longer something contained in the system alone. It has been spread, smeared, diluted across the whole environment, and from the point of view of anyone looking only at the system, it is gone. The possibilities can no longer interfere. They behave, to every available test, as if they were separate, distinct, classical alternatives, each one going its own way, no longer woven together into a single, shimmering quantum whole. This is decoherence, the rapid, relentless leaking of quantum overlap into an environment too large and too scrambled ever to retrieve it, and for large objects it happens almost unimaginably fast, far faster than any eye could catch. And decoherence explains a great deal, more than enough to see why the community greeted it with such enthusiasm. It explains why we never encounter a cat both alive and dead, because the moment such a superposition began to form, the cat's overwhelming entanglement with its environment, the air, the light, its own warmth, would destroy the overlap between the living and the dead branches in a span of time so short it has no meaning, leaving the two as cleanly separate alternatives, never interfering, never shimmering, just one or the other. It explains why the large world looks classical while the small world looks quantum, because tiny isolated systems can hold their superpositions while large entangled ones cannot. It even explains why certain kinds of states, like definite positions, are the ones we always find, because the environment, in monitoring its surroundings, naturally singles out those stable, enduring states and washes away the strange combinations. The movable boundary, the undefined cut between quantum and classical, suddenly has a physical mechanism behind it. The cut sits where it sits because that is where decoherence has done its work. For a while it seemed, to many, that the measurement problem had finally been dissolved, that there was no need for any mysterious collapse, that the appearance of a definite classical world emerged naturally and rigorously from the ordinary physics of systems bleeding their quantum character into their surroundings. The problem that had haunted the theory for half a century looked, at last, as though it might simply dissolve into the dynamics of the environment. And it must be said clearly that decoherence is not a speculation or an interpretation in the way the others are. It is established physics, worked out in rigorous detail, and confirmed in delicate experiments that watch superpositions fade exactly as the theory of decoherence predicts. Faster for larger systems, slower for well-isolated ones, in precise quantitative agreement. Experimenters have learned to hold small systems in such careful isolation that decoherence is held off long enough to keep a superposition alive and visible, and then to watch it die on schedule when the isolation is relaxed. So, this is not a story someone tells in order to feel better. It is real, measured, reliable physics, and it genuinely explains the emergence of the classical world from the quantum one in a way that nothing before it could. That is exactly why its limitation matters so much. The disappointment is not that decoherence is wrong, it is right. The disappointment is that being right about everything it addresses still leaves the central question standing, because the central question was never about the appearance of distinct alternatives. It was about why only one of them is ever real. There is one more thing decoherence gets right that deserves mention, because it sharpens both its success and its limit. It explains not only that the possibilities stop interfering, but which states survive as the stable alternatives. Out of all the bizarre combinations the mathematics allows, the environment, by constantly interacting with a system, naturally picks out a particular set of states as the durable ones, the states that get copied cleanly into the surroundings rather than smeared away. For everyday objects, these turn out to be states of definite position, which is exactly why the classical world we see is a world of things in definite places rather than things in strange, superposed locations. This is a real and satisfying result. It tells us why the alternatives that emerge are the familiar ones. But notice that it still only tells us which alternatives, not which single one becomes actual. It refines the menu, specifying that the choices are sensible classical options rather than strange quantum ones, and it still does not make the selection. Even the best of what decoherence offers stops one step short of the only step that would close the problem. But look closely at what decoherence actually delivers, and the floor gives way beneath the relief. Decoherence explains, with full rigor, why the different possibilities stop interfering, why they cease to overlap, why they come to look like separate, distinct, definite alternatives rather than a single shimmering superposition. It transforms the haze into something that behaves, for all practical purposes, like a list of classical possibilities, each with its weight, no longer blurred together. And that is an enormous achievement. But notice exactly what it has and has not done. It has given you a list of separate possibilities. It has not crossed off all but one of them. The cat, after decoherence, is described by a state in which there is a definite living branch and a definite dead branch, no longer interfering, cleanly separated. But both branches are still there. The mathematics, followed honestly, still contains both. Decoherence has explained why you do not see them blurred together into a shimmering whole. It has not explained why you see only one of them at all. The selection, the singular fact that the cat you find when you open the box is alive, this one, and not the dead one that is equally present in mathematics, is exactly the thing decoherence does not touch. It produces the menu. It does not make the choice. It tells you why the alternatives look like genuine, separate alternatives. It is silent on why one alternative, and only one, becomes the reality you actually experience. This is the quiet, deflating truth at the center of the decoherence story. It dissolves part of the measurement problem and leaves the deepest part standing, perhaps even harder to see now because it is so well hidden. The appearance of a definite classical world is explained. The achievement of a single definite outcome is not. Decoherence converts a visible superposition into what looks like a set of distinct classical possibilities. But a set of possibilities is not a single actuality, and the gap between the two is precisely the original mystery, untouched. Why this outcome and not that one? Why, out of all the branches the mathematics still contains, is there only ever one that you live? Decoherence, for all its real power, has no answer. It explains why the question is hard to notice. It does not answer the question. The community that embraced it as a solution had, in a sense, mistaken a profound clarification of the appearance of collapse for an explanation of collapse itself. The selection problem remains exactly where it was, at the very heart of the theory, as unsolved as it was the day the collapse rule was first written down. To put the limitation as plainly as it can be put, decoherence changes a superposition that visibly shimmers into a collection of possibilities that no longer shimmer and therefore look, to anyone examining the system, like ordinary classical alternatives. But looking like classical alternatives is not the same as being a single classical fact. A weather forecast that gives a 70% chance of rain and a 30% chance of clear skies has handed you a clean list of distinct, non-interfering possibilities with their weights. And that is a genuinely useful thing, but it has not made the sky do anything. It is still a statement of what might be, not of what is. Decoherence delivers exactly that kind of list, rigorously and beautifully, and then it stops. The step from the list of weighted possibilities to the single thing that actually happens, the step that the collapse rule performs by sheer decree, is the step decoherence cannot take. It clarifies the menu with perfect rigor, and leaves the choosing of the meal completely unexplained. And so, after a century of this, we are left with a conclusion that is hard to absorb because it cuts against everything our success with the theory would lead us to expect. Quantum mechanics is the most accurate, most thoroughly tested, most spectacularly successful theory in the history of science. Its predictions have never failed. The technology built upon it surrounds you and works without fail. And yet, when you ask what this theory says the world actually is, when you ask it to describe the reality behind the flawless predictions, it returns an answer that does not match the world you live in. The equations, taken at face value and followed honestly, describe a smoothly evolving wave that never collapses, that contains every possibility at once, that branches and spreads and entangles, but never, ever reduces itself to a single definite fact. That is what mathematics describes. And your experience, every waking moment of it, is exactly the opposite. You experience a single, definite, particular world, one outcome, one reality. The cat is alive or it is dead. The needle points at one reading. The light arrives at one place. Your entire lived experience is of the singular, and the theory's deepest description is of the plural, the superposed, the uncollapsed, and after 100 years, no one has been able to bridge the two. Consider what that means, slowly, because it is easy to say and hard to truly take in. The disconnect is not a small gap in an otherwise complete picture. It is a contradiction at the foundation. Either the equation is incomplete and there is some additional piece of physics, not yet discovered, that genuinely collapses the wave and selects a single outcome. in which case our most fundamental theory is missing something essential. Or the equation is complete and there really is no collapse, in which case reality is an unimaginable multiplicity of branches, and your sense of living in a single definite world is a kind of local illusion, true only within your branch. Or the wave was never real to begin with, only a summary of our information, in which case the theory tells us nothing at all about what the world is doing when we are not looking, and the definite reality we experience floats unexplained above a mathematics that declines to describe it. Each of these is a way of saying the same uncomfortable thing. The reality you are living in, the single definite world of your direct and constant experience, is not the reality that the most successful theory in physics describes. The map and the territory have come apart and no one has been able to put them back together. Whichever of these uncomfortable options is true, and perhaps it is none of them, and the answer is something no one has yet imagined, they share a single startling consequence. The theory we trust the most, the theory we have tested most severely and found most reliable, is a theory whose own description of reality we cannot reconcile with the reality we directly experience. We are in the strange position of possessing an oracle that answers every question we put to it correctly and yet cannot be made to tell us what it knows. We can ask quantum mechanics what any experiment will show, and it will tell us, and it will be right. We cannot ask what the world is, and receive an answer we can live inside. The success and the mystery are not in tension with each other. They are the same fact seen from two sides. The theory works so perfectly precisely because it predicts the outcomes of measurements, and it remains so mysterious precisely because it will not say what a measurement is, or what becomes of reality when one occurs. You can feel, if you let yourself, how unusual a circumstance this is for human knowledge. And most of what we understand, the better our theory becomes, the clearer our picture of the world becomes with it. A good account of disease tells us what disease is. A good account of heat tells us what heat is. Understanding deepens into a vision of how things actually stand. Quantum mechanics breaks that pattern completely. The better it has become at predicting, the more thoroughly it has confirmed that our picture of what underlies the predictions is missing or mistaken. A century of refinement has sharpened the predictions to perfection and left the picture in ruins. We have never known exactly what will happen and understand so poorly what is happening. The instrument grows finer and the view through it grows stranger, until we are left holding the most precise description ever written of a reality we cannot recognize as the one we live in. There is a temptation, facing this, to assume that the answer must be just around the corner, that surely a problem so central will yield to the next clever idea, the next experiment, the next generation of brilliant minds. But the measurement problem has worn down a century of clever ideas and brilliant minds without surrendering. It is not unsolved for lack of attention. Some of the deepest thinkers who ever lived have stared directly into it and come away with interpretations that, however ingenious, each demand a sacrifice no one can prove is the right one to make. The problem has the peculiar character of being perfectly clear and yet utterly resistant. Everyone agrees on mathematics. Everyone agrees on what the experiments show. The disagreement is about what it all means, about what is really happening when the haze becomes a fact. And on that question, the theory itself is silent, offering its flawless predictions while withholding, completely, any account of the reality behind them. We have a perfect instrument and no idea what it is touching. It may help to remember that physics has lived with deep mysteries before and made its peace with them for long stretches, sometimes for centuries, before a resolution arrived, and that sometimes the resolution never came in the expected form but arrived instead as a complete reimagining of the question. It is possible that the measurement problem is like this, that it will dissolve not when someone finds the missing rule, but when someone finds a new way of thinking that makes the old question seem malformed. It is also possible that it is trying to tell us something we are not yet ready to hear about the nature of reality, or of observation, or of the relationship between the two. What is no longer possible is to pretend the problem is not there, or that it has quietly been solved, or that it is merely a matter of philosophy with no bearing on physics. It sits at the foundation of our best theory, fully exposed, 100 years old, and patient. What we can say, with certainty, is that observation is doing something. Whatever observation is, however we should understand it, something happens when a quantum system is measured that does not happen when it is left alone. The spread of possibilities, which under the smooth rule would evolve forever without resolving, somehow yields, in the presence of a measurement, a single definite outcome that you then experience as the simple fact of the world. The smooth equation does not do this. Decoherence does not fully do this. No interpretation does it without paying a price that may or may not be the true shape of reality. But it happens. Every time a measurement is made, the many become one, and we cannot say how or why, or by what mechanism, or even what exactly qualifies as the measurement that triggers it. Observation reaches into the haze and brings back a fact, and the reaching is real, and its nature is unknown. It is a curious kind of certainty to be sure of an event and ignorant of its nature at the same time. We are as certain that observation does something as we are of anything in science, because we see its effect in every experiment ever performed. And we are as ignorant of what that something is as we are of anything in science, because no rule we possess describes it. Certainty and ignorance, side by side, about the same single physical act. The doing is beyond doubt. The nature of the doing is beyond reach. That is the precise condition the measurement problem leaves us in. And here is the part that should settle over you as the night deepens, the part that turns this from an abstract puzzle in a distant laboratory into something intimate and immediate and yours. This is not rare. It is not confined to careful experiments with detectors and screens. It is happening, right now, continuously, everywhere that anything is being observed, and that includes the quiet act of your own perception in this very moment. The light around you, the faint glow of whatever you can see, is made of countless particles of light, and each one of them, before it reaches you, carries its own spread of quantum possibility. And then it strikes the back of your eye. It lands on your retina, it is absorbed, it is measured, and in that instant, its haze of possibility becomes a single definite event, a single point of light registered, a single fact delivered into your scene. This is happening millions upon millions of times every second that your eyes are open. Every photograph your eyes are taking of the world, every glance, every moment of sight, is built from an uncountable cascade of these tiny collapses, each one a small instance of the very mystery that has defied physics for 100 years, each one a place where the spread of possibility becomes the single definite world you see, and it is not only your eyes. Every interaction by which the world makes a record of itself, every place where something definite comes to be, where before there was only possibility, is another instance of the same unexplained event. The warmth of a surface registering the light that fell upon it, the faint trace left in a leaf by a particle of light it absorbed, the countless small settlings of the possible into the actual that are happening everywhere, all the time, throughout the entire physical world, in numbers beyond any counting. The universe is, in this sense, continuously resolving itself, moment by moment, from a spread of what might be into a fabric of what is, and the mechanism by which it does so, the thing that turns the many into the one, is the very thing we cannot explain. You are surrounded by it. You are made of it. It has been the quiet background of every moment of your life. You are not observing the measurement problem from the outside. You are performing it constantly, with every act of looking, in the most ordinary and continuous way imaginable. The deepest unsolved question in all of physics is not happening somewhere far off. It is happening behind your own eyes, in the gentle, steady work of seeing the room around you, in the arrival of each particle of light at the surface of your retina, where the uncountable haze of what might be becomes, again and again, the single quiet fact of what is. We do not know what observation is. We do not know what it does or how it does it, and it is doing it now, in you, in the simple persistence of your own sight, turning the spread of the possible into the definite world you have lived in all along. So let your eyes rest, and then let them close, and notice that the question does not close with them. Even in the dark behind your eyelids, the world goes on resolving itself, fact by fact, observation by observation, becoming definite for reasons no one has ever been able to name. The haze becomes the world. The many become the one. It has been happening your whole life, in every instant of your seeing, and it is happening still, quietly, continuously, in the deepest mystery, hiding inside the most ordinary thing you do. Rest in that. The problem physics could not solve in 100 years is the same gentle act that has been showing you the world since the day you opened your eyes, and it asks nothing of you now but that you let it carry you, unsolved and quiet, down into sleep.